Welcome back. We're talking about stochastic gradient descent, and we want to find a way to reduce the variance so that we can use the self-tuning property in the setting where we have smooth and strongly convex function in order to recover the linear convergence that we had in the deterministic setting. So briefly, here is the setting that we're considering. We're trying to minimize a function f of x that has this structure. 1 over n times the sum of fi of x. As we've mentioned before, empirical risk minimization is a primary motivation for this setting. In particular, I'm looking at the setting where each fi is smooth. And the overall function f, not individually, but the overall function f is alpha strongly convex. A simple case that you can have in mind as a motivation for this is ordinary least squares. Minimize over x, 1 over n times the sum of ax minus y squared. Writing this out, this function is equal to 1 over n times the sum over the number of rows of the matrix A. I'm using AI transpose to denote the row vector, and it's the ith row of A, x minus yi squared. So each one of these is my function fi. And if you look at it, you'll see that each fi is individually smooth, but each fi is not strongly convex. However, if n is bigger than the number of columns of A, then this function will be strongly convex. So what we've seen repeatedly in a number of lectures that where we discussed convergence rate of gradient descent for smooth and strongly convex functions is that in addition to strong convexity, what we need is smoothness. So just as a brief recap, strong convexity is, if you recall, a lower quadratic bound on the function. This guarantees that if I'm far away, my gradient is very big, and so when I'm far away, I'm making very rapid progress towards the optimal solution. What happens when we're very close? Well, strong convexity isn't going to do that much for us because our function has flattened out. What we need is smoothness. Smoothness tells me that as I approach the optimal solution, my gradient goes to 0, and therefore I don't have to reduce my step size, and I won't overshoot. Whereas if that's not the case, if I don't have smoothness, if my gradient of f of x does not go to 0 as x goes to x star, this is our canonical example of this is the absolute value function, then even when I'm very close to the optimal solution, unless I'm taking a very, very small step size, I'm just going to be overshooting back and forth, and I'll never get very close. So we need these two properties together. There's no issue here with strong convexity. If we're very far away, we'll see that we'll make good progress towards the function. That's not the big problem with SGD. The problem with SGD that we've seen repeatedly, both in pictures and in actual fact in the algebra of our analysis, is that we have to take a small step size with SGD as we've seen it, because otherwise we're going to overshoot. Again, the whole problem is that the subgradients that we've seen, the magnitude, expected square of the subgradients does not go to 0 even when I take them closer and closer to the optimal solution. Even when I take them at the optimal solution, this is not going to happen. So we need a different element. Last lecture we considered mini-batch. Mini-batch has many advantages, but it's not going to give us the self-tuning property. We need a different idea. The key idea is to reduce variance by recentering the subgradient. Remember that even though, let me quickly write down our function here, even though our main motivation is to look at subgradients, stochastic gradients that have the form gradient of fi of x, this is not the only choice that we can make. So instead, the key observation that we're going to exploit is that For any 2 points, I'll call them x and z. For any 2 points, x and z, let's look at this g tilde. I'll suppress for now the dependence on z. Gradient of fi, I as usual is my uniform random variable, at x, minus, so this is the new term, and this will be my recentering term, minus the gradient of fi, this is the same I, it's not a different random variable, it's the same one, and that's critical, evaluated at, not at x, but at z, minus the full gradient evaluated at z, is also a stochastic gradient. This is also. What do I need to do to verify that something is a stochastic gradient? Well, all we need to do is make sure that its expectation is in fact equal to the full gradient of f at x. Let's just check this. So I need to check that the expectation, and what's the expectation over? It's over the randomness. The randomness is I. Maybe I should just make this explicit here. Again, as before, I is a uniform random variable on 1 to n. So the expectation over I of g tilde of g tilde of x, make sure my handwriting is clear here. This is just equal to the expectation of these 3 parts. Expectation of the gradient of fi of x minus the expectation of the gradient of fi of z minus, well, the gradient of f of z doesn't have any randomness in it, so it's just gradient of f of z. This first term, as we've shown by careful computation in previous lecture, is just equal to the gradient of f of x. By the same token, the second term is equal to the expectation of, is equal to the gradient of f at z. And the third term is just itself. So indeed, this cancels, and I have the gradient of f of z. So we're going to exploit this idea of reducing variance by recentering by giving a different SGD algorithm. This algorithm is called SVRG, and it stands for Stochastic Variance Reduced Gradient Descent. And it's similar to a number of different algorithms that are in the literature, in particular SAG and SAGA. We're not going to talk about those in detail right now. So this SVRG algorithm has an outer loop and an inner loop. In the outer loop, on the kth iteration, we set x1 equal to yk, and then we move to the inner loop. And we repeat this for t equals 1 to capital T. X t plus 1 is equal to, so this inner loop is just my SGD algorithm. So xt plus 1 is equal to xt minus my step size times my stochastic gradient. But I'm going to use the stochastic gradient that we just saw on the previous slide. This is my recentered stochastic gradient. And the 2 points I'm going to use, x and z, they're going to be xt and yk. So this is going to be the gradient of fi evaluated at xt minus my recentering. The recentering is going to be computed at y. So minus the gradient of fi, the ith component, again this is the same I, evaluated at yk, minus the full gradient of f evaluated at yk. Once this inner loop completes, we update y. yk plus 1 is equal to 1 over t times the sum of all of the iterates generated by this trajectory of the inner loop. And there's other ways to update y, but for us, this is how we're going to do it. So let's talk about this for a moment. What are the differences between this algorithm and SGD? We see that we have, of course, we have an outer loop and an inner loop. The inner loop is just SGD. If we think about the effort it takes to compute the inner loop, what does it need? Well, y is not changing in the inner loop. So this gradient of f of yk doesn't need any additional computation. All I need to compute this inner loop is to compute at every instance, I need to compute the stochastic gradient of at xt. So this is, the inner loop has exactly the same computational effort as SGD. The outer loop, however, is much more expensive. The outer loop requires computing a full gradient at y. So let me just note this because this is an important feature of the algorithm. Inner loop, each iteration requires the same effort as our previous SGD algorithm. In other words, we just need to compute the gradient of fi at xt. Yk does not change. However, the outer loop is expensive. It requires a full gradient computation. Just like if we were doing deterministic full gradient descent. So this idea of stochastic variance reduced gradient algorithm is to try to take advantage of both worlds. We're going to take advantage of the speed of stochastic gradient descent by having a fairly large inner loop, and hopefully we're going to take advantage of the self-tuning property of gradient descent, but doing this with less computation by having this outer loop that happens only once in a while. The key that we want to show is that the variance of our stochastic gradient goes to 0 as we approach the optimal solution. This we're going to show with this key lemma, which is called the variance reduction lemma, aptly named. And it goes as follows. So let's let f1 to fn be exactly as stated above. Each is individually beta smooth. We actually don't need strong convexity in this case. We don't need this yet. And again, as before, I is uniform on 1 to n. Then, the expectation of the gradient of fi at x minus the gradient of fi at x star is going to 0 as x goes to x star. And specifically, it's upper bounded by twice the smoothness parameter times f of x minus f of x star. So note the key point here is that we're not comparing, this is not a statement about the gradient of fi. So in particular, the gradient of fi at x may not be small. When x equals x star. This is just saying that this difference goes to 0 as x goes to x star. And by itself, it's actually pretty intuitive. So the whole point is that you can see that that inside the expectation and inside the squared norm, I have the gradient of fi of x minus the gradient of fi of x star. So it's actually not too surprising. It's not unintuitive that we should have something like this. So let's, for the sake of completeness, see the proof of this variance-reduced lemma. Let's let gi, I'm going to define a new function, gi of x equal fi of x minus fi evaluated at x star plus the gradient of fi, also evaluated at x star, times x minus x star. If you see what's inside the brackets here, this is just the linear approximation of the function fi at the point x star evaluated at x. So by our basic property of convexity, that means that this is always greater than or equal to 0, just by our usual convexity here. And of course, gi is also convex, and it's also smooth. So why is that? Well, gi here is equal to fi of x minus a linear function. And subtracting a linear function cannot change your smoothness, and it cannot change your convexity. So let's think back to one of our earlier lectures on smooth functions. We had proved a very important property. We call h as a generic convex smooth function. If h is convex and beta smooth, then we had showed that h of x minus gradient step minus 1 over beta times the gradient of h of x is upper bounded by h of x minus 1 over 2 beta times the norm squared of h of x. This was one of the key ways in which we exploited smoothness in order to show faster rates of convergence for smooth convex functions. Let's apply this to g. And let's also use the non-negativity of g. So putting this together, we've got that 0 is less than or equal to gi evaluated anywhere, and in particular evaluated at x minus 1 over beta gradient of gi of x. So, and this in turn, just like the inequality above promises, is less than or equal to gi of x minus 1 over 2 beta times the gradient of gi of x squared. This implies, moving this over to the left, that minus gi of x is less than or equal to minus 1 over 2 beta times the gradient of gi of x squared. And rearranging this implies that the gradient of gi of x squared is upper bounded by 2 times beta times gi of x. All I did is I just moved the norm to the left and moved g to the right, multiplied through by 2 beta. Okay, now let's just plug in for the gradient of gi of x. So looking at what gi is, again, this is up here. So what is the gradient of this with respect to x? So writing that out, I've got the gradient of gi of x. This is just equal to the gradient of fi of x minus what happens to the next term in gi. That's fi evaluated at x star. That's a constant, so that goes away. And then I've just got a linear term. Remember, x star is, I'm not taking the gradient with respect to x star, but rather x. So I'm just subtracting the gradient of fi of x star. That's the gradient of gi of x. And so this inequality right here, this tells me that this is upper bounded by 2 beta times fi of x minus fi of x star plus gradient of fi of x star transpose x minus x star. And therefore, taking the expectation, this tells me that I basically have the variance reduction lemma. the expected value of the gradient of fi, I've now changed to, so let me make this clear, this is important. So far I've been doing everything for a generic I, but now if it holds for every I, it also holds for the expectation over I. Capital, because this denotes a random variable. The gradient of f capital I of x minus gradient of f capital I at x star is less than or equal to what happens here on the right when I take the expectation. The expectation on the right, what's the expectation of f capital I? Let's just do that quickly here. The expectation over I of f capital I of x, well, this is just equal to the sum of possible outcomes I could take plus the probability of those outcomes. Probability that I takes any of the individual values from 1 to n is 1 over n, and the value it could take is fi. So this is just f. Okay, just a little reminder. So what happens here? Applying this, I have 2 beta times expected value over I of fi of x, that's just f of x, just what we computed, minus expected value of fi at x star. Similarly, this is just f of x star. And then what? What is the expected value of the gradient of fi evaluated at x star? Well, it's the gradient of f evaluated at x star, which is equal to 0. So that goes away. And so we have exactly what we wanted to show. So again, let's overview the main features of this. This is controlling the expected value of the square of not the gradient at a random point, but a recentered gradient. And it's saying that that recentered gradient, stochastic gradient, is going to go to 0 as x approaches x star. And in particular, it's telling me how it's going to approach 0. It's going to approach 0 just as fast as f of x approaches f of x star. All right, let's see how we're going to use this in the result. So the theorem says the following. Again, let me repeat a little bit about what the setting is. F is equal to 1 over n times the sum of fi of x, as before. Each fi is smooth, and the overall f is strongly convex. So fi is beta smooth for each I, and f is alpha strongly convex. Now let's suppose that we run our algorithm. What do we need for SVRG? We need to specify the step size eta for the inner loop, and we need to specify how many iterations are there going to be in the inner loop. Those are the only 2 parameters I need to specify the algorithm SVRG. So the SVRG algorithm with step size eta, which is equal to 1 over 10 times beta. You see, now these numbers 10, you know that when I choose a particular constant, it's always going to be to make the final calculation turn out nicely. The key thing that you should be focusing on is that the step size is 1 over beta, and that's exactly the step size that we have when we have a smooth function. So already now you can see a big difference from when we were doing stochastic gradient descent, either for mini batch or for mini batch size of 1, so the original version of SGD that we presented. There, if you look back to the theorem, the guarantee is when eta scales like 1 over the square root of t. And in the presence of strong convexity, we needed eta going down, actually decreasing, like 1 over the iteration, approximately. So this is something different, and this is what we should be focusing on. This should be telling us that we are back in the territory of smooth and strongly convex functions, and we better expect the self-tuning property, otherwise we're not going to get any kind of convergence that we like. Okay, so step size 1 over 10 beta. Again, the key is the 1 over beta. And the number of iterations of the inner loop, this is the second parameter that we need to specify SVRG. Inner loop size, t, is what we called it when I specified the algorithm, is going to be some multiple, again, the multiple is not so important, times beta divided by alpha. This is the condition number. The smoothness divided by the strong convexity. The closer this is to 1, we know the better our life will be. Remember that this also appeared in our analysis of gradient descent. We're going to get back to this later when we compare all of the methods that we've discussed so far. So in this setting, if f satisfies these properties, if we run SVRG with these two parameters, then after s plus 1 iterations of the outer loop, so s plus 1 runs through the entire algorithm, then the final solution produced, y s plus 1, is going to have an expected suboptimality that scales as follows. So the expectation of f of y s plus 1 minus f of x star is bounded above by 0.9 to the s times f of y of 1 minus f of x star. Let's discuss briefly the main features of this result. We see here that we have s being the number of outer loops. So this is the number of full gradient computations we're going to take plus the cost of every inner loop. So we need to discuss this in bigger detail, and we'll do that later when we're comparing the algorithms. The other thing you should note, however, is that key features here is, one, we have our linear convergence. And for those of you that remember the details of the linear convergence guarantees we had for gradient descent for smooth and strongly convex functions, you should be interested that alpha and beta don't seem to appear here. In fact, we have a 0.9. So of course, the fact that it's exactly 0.9 is not in itself significant. If I took a step size that wasn't 1 over 10 beta, but was 1 over 9 beta or 1 over 11 beta, and my inner loop size t scaled in a slightly different, was a different constant times beta over alpha, this 0.9 would change. But the key fact is that by having an inner loop size that depends on beta over alpha, my convergence rate, the number of outer loops I need to take, no longer depends on beta over alpha. When we look at a detailed comparison in the next lecture of gradient descent versus stochastic variance reduced gradient descent, we're going to see that this is important. So this linear convergence, beta over alpha, does not appear in the convergence rate. So this is important. We're going to keep going and get through the proof of this SVRG result. It's going to use the variance reduction lemma that we showed earlier, and that will be in some way the key to this. We're going to analyze one step. So we're going to one step of the algorithm and show that in one step of the algorithm we get a 0.9 factor reduction in the suboptimality, and that will be enough because that tells us that if we repeat it s times, we get 0.9 to the s reductions. So it's enough to show that the expected value of f of y s plus 1 compared to f of x star is reduced by a factor of 0.9 compared to f of y s minus f of x star. And again, just repeating that s times would give us exactly the result we want. So this will help us simplify notation a little bit. We won't have to carry around s and subscripts and superscripts. So recall that we have y s plus 1 is equal to 1 over t times the sum of xt, where xt is produced in the nth iteration of the inner loop. So if I really wanted to be careful, I would have to write x superscript s, but I hope that it's clear here and it'll help us with our notation. So in other words, it'll help simplify a little bit. So I'm going to write xt instead of xt superscript s, and I'm going to write just plain old y instead of y superscript s. Okay, so let's get to it and see where this variance reduction lemma is going to kick in. So the proof is going to proceed very similarly to a proof of, not surprisingly, convergence of gradient descent in the presence of smoothness and strong convexity in the deterministic, or in other words, in the full gradient case. xt plus 1 minus x star is equal to xt minus eta. So again, xt, I'm not talking about the inner loop. Okay, so xt plus 1, how does that differ from xt? It differs by one SGD step, not a full gradient. So it's minus eta, xt plus 1 is equal to xt minus eta times my recentered gradient, my recentered stochastic gradient. So this is the gradient with respect to fi. I'm going to add a subscript t here just to remember that this was the I randomly chosen at the tth iteration of the inner loop. xt minus my recentering. So minus gradient of f, same it, but evaluated at y. This is the y that doesn't change. Right? This is the y from the outer loop. Again, I'm not going to write ys, I'm just going to write y. Minus the full gradient of f, again, evaluated at y. Oops. So this is xt plus 1, what I've written, and I still need my minus x star. I'm going to expand this quadratic, as we've done many, many times before at this point. So I'm grouping xt with x star. Xt minus x star squared. I've got minus twice the cross product plus the middle term squared. So minus 2 eta times gradient of fi of xt minus gradient of fi of y plus, I'm just distributing the minus sign, gradient of fy, transpose xt minus x star, and I also need this term squared. For ease of notation, let me call this term here vt, so I don't have to keep writing this out too much. So then I've got this term again squared, and I'll use my vt here just so I don't have to write it out again. So this is going to be my eta squared times vt squared. So this is, again, just rewriting these terms, xt minus x star squared. I'm going to call this term A, minus twice eta vt transpose xt minus x star. I'm going to call this term B, and plus eta squared times vt squared. I'm going to call this term C, and this is my variance term. If you look back to the proof of just SGD, it started in exactly this way. And this term C is what we were not able to get rid of. It wasn't going to 0, and that's what forced us to take a very small step size eta, because we had accumulated t copies of this variance term that wasn't going to 0, and the only way to make that small is to make the coefficient in front of it small. I had to take eta to be on the order of 1 over square root of t. Okay, so now what we're hoping is that this variance term, because I'm using a recentered gradient, stochastic gradient, is going to go to 0 by itself. So this is the key. This is what we should be looking for. So let's go to that first, since this is the critical part, and see how we can control that term. So let's look at C, just what we had before. Expected, and I'm going to look at its expectation. So this is expectation over IT of VT squared. Okay, writing out what that is, this is equal to the expectation of the gradient of FIT, evaluated at xt, minus the recentering, gradient of FIT at y minus the plus, I've distributed the minus sign, plus the full gradient of f at y, this squared. Okay, I'm going to add and subtract the gradient of fi at x star. So I'm going to subtract the gradient of fi at x star and add it back. And now I'm going to use the property that a plus b squared is less than or equal to twice a squared plus twice b squared. So this is going to be upper bounded by twice the expected value over it of gradient of fit of xt minus gradient of fit of x star. This is the first x star that I added and subtracted, plus twice the expected value of the other term that was left. This is my fi of y, gradient of f of y, and then the other gradient of fi valued at x star. So this is the gradient of fi at y minus the full gradient at y minus the gradient of fit evaluated at x star. Now, note here that this term here, what is its expected value? What's the expected value of the interior, of the inside? I can't pass expectation into the interior. I'm asking for, we'll see why we're asking this question. So what's the expected value of this? Well, the expected value of this, the expectation of the inside, is actually 0. So expectation is 0. So why is that? Because the expectation of the first term is the full gradient of y. Then I'm just subtracting the full gradient of y. And then I've got the expectation of fit at x star, which is just the full gradient of f evaluated at x star, which is 0. So because of this, I'm going to use the fact that the expected value of any random variable minus its expectation squared is less than or equal to the expected value of y squared. In other words, I'm going to make this whole right-hand side bigger by dropping this term. I'm going to drop this. Okay, and that follows, I'll be able to do that just by this fact that I wrote down. So this in turn is less than or equal to the same first term, expected value of it, gradient of fit xt minus gradient of fit x star, this squared, same as before, nothing changed, plus twice expected value over it of just the first two terms, gradient of fit of y minus gradient of f of y squared. Oops, sorry, I've made a mistake here. I'm dropping this term because this term is the expected value of the first and third terms. fit. So the expected value of fit of y is equal to gradient of f of y. And the expected value of the third term is 0. So the expected value of the first and third term is equal to the second term, and that's why the expectation of the overall thing is 0. So I'm dropping this second term and only making things bigger. Now what can I do? We need to flip back a little bit so that you can see that this is exactly where I'm going to use my variance reduction lemma. And I'm going to use it twice. So let's look at what we have. We have the gradient of fi evaluated at xt minus the gradient of fi evaluated at x star. And then the gradient of fi evaluated at y minus the gradient of fi evaluated at x star. So let's look back at our variance reduction lemma and see that this is exactly what we had. The variance reduction lemma promises me an upper bound on the expectation of the squared norm of the gradient of fi evaluated at some point x minus the gradient of fi evaluated at x star. So that's exactly each of the two terms that I have now have this form. And so I'm going to upper bound each of these two terms by twice beta and the difference of the f's. So I use our variance reduction lemma twice. And I get that this is upper bounded by 2 and another 2 beta, so 4 beta times f of xt minus f of x star. That's the first. And then I have a f of y minus another copy of f of x star. Okay, so much for term C. We have to now control terms A and B. Let's look at our term B. This was equal to twice eta vt transpose xt minus x star. And I want to control its expectation. So the expected value of twice eta times vt transpose xt minus x star, this is now my chance to use the fact that vt is a stochastic gradient. This recentering has expectation 0. This is equal to twice eta. By linearity, I can pass the expectation to the only thing that has randomness, which is vt, times xt minus x star, and this is exactly equal to the full gradient of f evaluated at xt. So this is equal to twice eta times the gradient of f of xt transpose xt minus x star. Whenever you see a gradient dot product with two different points, you should be thinking convexity. This is an upper bound on twice eta times f of xt minus f of x star. Term A is going to stay exactly the same. So putting it all together, I have that expected value of it of xt minus x star squared, xt plus 1, is lower bounded by a plus b plus c. We already had that result, and now we've upper bounded b and c. So this is upper bounded by a. A is exactly the same. A is just my xt minus x star squared term. My upper bound for b, that's sitting up here. So remember, we were subtracting. So as not to have confusion here, we're actually subtracting. We were subtracting b. So I'm subtracting something smaller. That's why this lower bound is useful in order to give me an upper bound. I'm subtracting something smaller. I've got my 2 eta f of xt minus f of x star. And then I've got term C, which we just bounded on the previous slide. This is 4 beta times f of xt minus f of x star plus f of y minus f of x star. All right, we're almost there. What am I going to use? What property am I going to use now? I'm going to use the fact, looking at, so now I'm going to just repeat this, or I'm going to iterate this algorithm, and I'm going to use, iterating this algorithm, I'm going to get that this is now upper bounded by, Actually, I'm not going to iterate quite yet. I have one more step. xt minus x star squared plus, minus 2 eta times 1 minus 2 eta beta times f of xt minus f of x star plus eta squared 4 beta times f of xt, f of y minus f of x star. So what just happened here? I've got an f of xt minus f of x star, f of xt minus f of x star. I just grouped these coefficients. So you see I have minus 2 eta, and I have my eta squared minus, times 4 beta. That's just what happened from this line to this line. This is actually an equality. So now, iterating this, I find that, so iterating this inequality, I get that the expected value of x t plus 1 minus x star squared is upper bounded by xt plus 1 became xt here, and iterating it will become xt minus 1, xt minus 2, while I'm summing all of these other two terms. So this is what we're looking for. So I'll have my x1 minus x star squared minus the coefficient 2 eta, 1 minus 2 eta beta, and now times the accumulation of all of those other terms. So this is the sum from k equals 1 to t of f of xk minus f of x star, plus that last term was just f of y minus f of x star. There's no t in it, so I just have the coefficient, eta squared 4 beta, and then just t copies of it, times what I had, f of y minus f of x star. So now a few things to observe in order to finish this up. First of all, observe that x1, which is sitting right here, is just equal to the previous y, because that's how I initialize every inner loop. I set x1 equal to whatever y I had. So I'm going to put y in there. And then I'm going to use the strong convexity of the overall function f. So by alpha strong convexity of f, I have that y minus x star squared is less than or equal to 2 over alpha times f of y minus f of x star. And if you don't remember how this goes, this is a good opportunity to go back and look at those lectures on properties of strongly convex functions to see how it is that we can get this upper bound using strong convexity. So this is what's going to happen to this first term. And finally, putting this now all together, I'm going to move this term over to the left-hand side. This is the term that I want to bound. This term here, because of 0.2 here below, is going to merge together with this final term, f of y minus f of x star. And putting this all together, what I'm going to find is that 2 eta, 1 minus 2 eta beta times the expected value of f, 1 over t, times the sum of xt minus f of x star is less than or equal to, and now this is just a product of, it's just accounting. You just need to trace through everything. Here's my 2 alpha times f of y minus f of x star. I need to add that to eta squared 4 beta times t. But I'm also dividing by t, so I've got my 1 over t, and this is my f of y minus f of x star. So this is what happened to this term and this final term. And this middle term moved over onto the left, so this is what we've got. dividing through by this constant, we finally get our result. So note that this was our next y. This was our, let's bring back s. This was y s plus 1. And I'm going to replace this with f of y s. I had dropped the s just to make my life notationally easier. And so what we have dividing through is that the expected value of f of y s plus 1 minus f of x star is less than or equal to some constant, which if you put everything together, you'll see that my specific choices for eta and for t make it simplify almost magically to 0.9 f of ys minus f of x star. This concludes the proof of SVRG. Next time, we're going to talk about how SVRG compares in terms of computation versus accuracy with plain SGD and gradient descent. We're going to pick this up next time.